Hello and welcome, I'm Ethan7878. Thank you for tuning into this video. What we're going to be doing today and what you see before you is a little bit different from my usual format in that this program that I'm going to be showing you is entirely text-based. We aren't touching on graphics today. Also, this program runs on a concept that's a little bit more practical to modern applications, and that's called machine learning and genetic algorithms, and I'll get into an explanation of how those work later on in this video. Well, let's get right into it. So we'll get started here, and this is completely text-based. My next video with the genetic algorithm will have a little bit of graphics in it, but in the meantime we'll just start with this. So what is a genetic algorithm? Well, we have our main method here, and then a population and a gene set, which is just like one person, one entity that has a bunch of genes. And well, basically what it does is you create a population and then rank all the people in that population based on how they perform a certain task or how well they perform a certain task. And then you pick out the best ones and build a new population based around them. And ideally, after enough generations of that, you'll have a population full of people that are really, really good at that certain task. And this is very useful in modern computing. A lot more useful than just drawing some shapes on the side of a ship anyway. But let's get started here. So as you can see, I have a few methods already planned out. So I have my main method. Of course, this isn't an applet. This is just text-based. And we have the population and our set of genes. So what should I start with? I think I'll start off with the gene set, because that's the simplest part of this program. So we're importing util because we're going to need random. And I'm going to store all of my genes in a string. So we'll do that. Again, we're going to need a random object. So you have our new random there. We're going to need the fitness, which I'll get to in a second. That's basically how you rank how well a certain member of your population is. And we're going to have the length of the genes, which might be a little bit redundant, but we'll get to that. We'll see about that later. So our first constructor, where we have gene set, and all we have to go on is a number of genes. So what we're going to do is gene len equals len, and then for each gene, I is less than that. Simple for loop here. And we're going to add a random character in a certain range. And I've calculated this ahead of time, so 32 plus rng.nextInt up to 95. And so this gives us a random character with an ASCII code between 32 and 126 or 127 or something like that, which is where all the meaningful characters are. You don't want like return characters and stuff in your string. So this will be all uppercase, all lowercase, all numbers, and some other characters like punctuation and stuff in there as well. So a pretty wide range. And then our second constructor, this will be used when we want to make another set of genes based on a set of genes that we're inputting. And so all we do is this.genes equals genes, and we can do that because we're passing in a string and not one of our objects. Next up, since we're going to be comparing this set of genes to a string that we want it to guess, we're going to have a fitness function. So I'm going to make that no space, fitness, and we're going to have a goal that we're trying to work towards, and that'll all be explained in the main method. So we have 0 matches at first, and then for each character in the goal, we're going to be comparing that to each character in this object's genes. So the way we do that is if this dot genes dot character at I equals goal dot character at I, and we increment matches by 1, and once we've ran through all the string, this dot fitness equals matches divided by the length of our genome. So what it'll do is it'll create a number between 0 and 1 as a percentage, so 1 being it matches the goal 100%, and 0 being it matches at 0%, and 0.5 being like half the characters match. Next up, we're going to need a way of picking which gene sets we're going to use in our populations as we reproduce them. So I'm going to have an algorithm that basically picks it from a pool. And this is a very simple method. Most of this algorithm is done in the population object. But all we have to do is return whether the next double of RNG is less than this dot fitness. So RNG.nextDouble creates a random double between 0 and 1. And if we have a high fitness, then there's a very good chance that the next double will be below that fitness. If we have a low fitness, then there's a low chance that it'll get returned. And finally, of course, we don't want our algorithm to get stuck if there's one character that just never turns out to be correct. So we want a bit of mutation in there, because there's always room for improvement. So we'll have our last method that we need here with mrate, or mutation rate here. And what that'll do is it'll run through this genome. So a for loop like so. And we're just going to use, again, RNG.nextDouble. So if it's less than mutation rate, then we want to have a formula worked out here with substrings and stuff. So this dot genes dot substring beginning at 0 and going up to I plus again our formula for picking a character, which I'll just copy from up here, plus that, plus genes dot substring, and using math dot min I plus 1 and gene length. So what this will do is this will take the first part of the string plus a random character plus the last part of the string. And the reason we have math.min here is because if we were replacing the last character, well, there's no second part of the string, so it would be substring of basically nothing. And that's what this little one-line method does. So there we go, that's pretty much our gene set done. Now let's move on to the population. And how are we going to do the population? Well, the population is just an object that's responsible for holding a bunch of gene sets. It's responsible for managing all of our population. You can run a quick test actually, just to show. So gene set G, for example, is a new gene set of length 10, and we'll just print G dot genes, and you can see 10 random characters. And we could run it again, we'll get 10 other random characters. And eventually we're going to get that all this randomness to approach a certain goal. We'll get to that in a few minutes. So the population, we're also importing util because we're going to need some randomness. And again, the population is holding a bunch of gene sets. So I just call that pop. And the population will actually store the goal just for convenience. And again, gene length. So we have our population constructor here, and we're going to pass in how big we want our population and what the goal will be. Also, we're going to need a random object. So we'll save the goal to this object, and we can just calculate the length of the gene from the length of the goal, because of course we want to create gene sets that have the same size as the goal. If you didn't, then you could have a more complicated fitness function. I might do that later, maybe not. And now we want to make our population, so this dot pop is a new array of gene sets with the length of pop size. Now we want to actually fill this array, so I is less than pop size, I plus plus, and we'll say that the array at position I is a new gene set with that specified length, and then we want to calculate the fitness of that object. So again, calc fitness, and we'll just pass in the goal since we already have it. So what we're doing here is we're saving the goal, we're calculating how long the genes have to be, and then we create our population, and with the population, again, we're using this constructor here just to make a random string, and then we're using this here, calc fitness, and that's going to calculate how close this new random set of genes that we created is to the goal. So now I'll explain how pool selection works. You might have been wondering with this pool picked here. So pool select is basically how we're going to pick the best in our population. So in order to do that, so I'll have the public population next gen, and we have to account for mutations in here as well. So this is what's going to basically create a better generation each time. So we just create our population object. There's a new population. And that's why we saved all those variables earlier. So now we need to make sure that, and also return next while I'm thinking of it so I don't forget. So now we need to find a way to make sure that each element in the next population is better than the one before it. And in order to do that, so we'll run through each element in there. I could be using a for each loop technically, I guess, but anyway. So for each element, next array dot genes is this dot, and we're going to have a method called splice, and then at I dot mutate, we'll pass in the mrate, and next pop at I dot calc fitness, and we'll pass in the goal. So how does splice work? Well, splice is using something called crossover in genetic algorithms. And what crossover does is it combines two individuals in your population to make something hopefully better, but it might be also worse under certain circumstances. So splice is going to return a set of genes. And since it's just local, we can make it private. So private string splice. We'll have our string there, and it's just an empty string. And gene set parent 1 equals this dot pool select, and gene set parent 2 is this dot pool select. And so this is where pool selection comes in. So again, it's local, so I'll make it private. So private gene set pool select. And how this works, well, this is why it was so important to have our fitness be in between 0 and 1, and why this pool picked comes into play. So we're going to have a certain limit of tries, because if everyone has a fitness of 0, you're never going to pick anyone because they're all so bad. So we're going to have a do while and tries and then just an arbitrary number. In this case, I just picked this dot pop dot length. Keep things short. So we have a choice, this dot RNG, with the next integer lower than that. And now if this dot pop at choice dot pool picked, then we will return new gene set with that at choice dot genes. And so what this is doing is we're actually in this line creating a new gene set with the genes from the previous gene set, and we're returning it immediately. And then otherwise return a new gene set from a random element in the population. This dot pop dot rng dot next int up to this dot pop dot length dot genes. And so what this line is doing is saying return a new set of genes from some random spot in the population and using its genes, if that makes any sense. So there's our pool selection done. Now we need to go back to splice and finish that off. So we have our two parents sorted out, and now we need to just merge them in. So what we'll do is for each character in the new set of genes that we're going to need, what we're going to do, new genes plus equals, and then an inline if statement, so rng.next boolean question mark p1.genes@I or p2.genes@I, or car at I, actually. haven't touched Python in a year, but I still think you can access genes with the square brackets anyway. And then we just return new genes. So what this is doing is we have rng.nextBoolean, which will return a true or false. If it's true, then take the next character out of P1. Otherwise, take the next character out of P2. And then we add that to new genes, and then we return new genes. So that's this.splice done and over with. And now we just have to do just some convenient stuff. But we can already get this, I think we can already get started on the main method. So, what variables do we need to control our population? Well, we're going to need a goal. And the goal can have any characters as long as they have ASCII between that 32 and 127 boundary. Next, we're going to need the size of our population, which in this case, I don't know, let's make it 100. And the generation is 0. And then we're going to need double mutation rate equals 0.01, for example. And best fit, we'll start that off as 0, and I'll get to using that later. So, population P equals new population, pop size, and goal, again passing in those two, the size of the population and what you're working towards. So what this main method is going to do is each gene set is basically just a string, but you can't call it a string because the string is already taken. So it's just a string of characters. And we're going to start off with 100 randomly generated strings of the same length as this. And we're going to keep making a new population, and then for each new population, we take the strings that are closest to this, and we combine them together, we mutate them, we do whatever, and we come out with some strings that are a little bit closer to guess this sentence, hopefully. And we keep doing that over and over and over again until we actually do get a string that matches. And that's like the simplest example of a genetic algorithm. But it's good to learn. It's a good example for learning, basically. So, we have our population, and let's just say 10 times. So, we'll increment generation, and then population is p.nextgen with our double m rate. And, well, I need a way to output the best one, so I might as well work on it here. I thought I could get around it, but anyway. Whatever. For int I equals 0, I is less than p dot, or I is less than pop size. Dot genes. So it's mostly nonsense, but you can see there's a few, you got G's in the first characters, a few E's around. And if we run it 100 times, I think we'll get something a little bit better, and you can see the words guess sort of coming together. We almost have this, and then sentence is still a little bit disorderly. Let's run it 1,000 times. And yeah, now you'll see we have it almost nailed a few times. And you can play with the numbers a little bit, so I'll turn the mutation rate down, and then yeah, see we have it pretty much set, because sometimes what happens is you get it correct and then you mutate it away because the mutation rate is so high. So, and yeah, now that we have a lot more to pick from, the pop size being 1,000, you'll see that it's a lot more reliable at figuring out the sentence. And this can be any sentence, pretty much any length. It could just be whatever you want. And if you give it enough generations and enough population, then it'll pretty much figure it out. Oop. See? Pretty much perfect. And it's just the odd mutation here and there where it screws up. So now we just want to add some quality of life type of stuff. So that comes into the population just to make the output look a little bit nicer. So we'll have our gene set find best, and this will return the most fit member of the population. So max is 0, max index is 0, and we'll just run through the loop. So if the pop at I dot fitness is greater than max, then max equals this dot pop at I, and max I equals I. So we're just updating what the best one is. Dot fitness, of course. And then at the end, we just want to return pop at max I. This is finding the most fit gene set, just setting the maxes and then running through it and then returning it. Now, public double, max fitness, and this will return the fitness of the best one. Actually, I don't need this one. Never mind. I can just use find best dot fitness. So we'll get rid of this here, and we have our population P. And then what I can do is I can say while P dot find best dot fitness is less than 1. So while none of the elements have a fitness of 1, we want to be iterating through and making new populations. So gen plus plus P equals P dot next gen, pass in the mutation rate, and this is where best fit comes in. So if P dot find best dot fitness is greater than best fit, then we're just going to print we have a new best. So just a bit of formatting here, some general information. So what generation are we on? Well, that'll be just gen. And then plus, what else? Well, plus a new line, that would help. And then plus P dot find best. So I think this will pretty much work, and then let's just try that out. Oh, whoops. Find best dot genes. So at our first generation, we had something that's not too bad. second generation getting a little bit better, and then pretty much each generation there was something a little bit closer. Let's make our sentence a little bit longer. And you can see that you can get a little bit closer every time. Also, I should probably remember to increment best fit. I was just wondering there for a second. Equals p dot find best dot fitness. So there we go. Now only when there's a new best. So generations 8, 9, and 10, not really any improvement. Generation 11, suddenly there was an improvement. And another thing that I think you should print out is also p.findbest.fitness. Oh, plus maybe a space or something. Actually, plus a tab. So this fitness was 0.26, 0.315, 0.37, and you'll see as it goes on and on and on, we get closer to 1. So there you go, that's a basic genetic algorithm. All it does really is guess a predetermined goal, but it's a pretty simple example to learn. I hope you've been following along, and maybe you can try it out yourselves. So anyway, that pretty much does it for this video. Look forward to next week's video, where I'll be definitely improving on this and doing some really cool stuff with genetic algorithms. In the meantime, if you liked this video, if you enjoyed it, then please make sure you hit the like button before you leave. If you want to see more videos like this, then please subscribe and check out my channel. I have other videos based on programming. If you have any suggestions or feedback, then leave those in the comment section down below. And anyway, thanks for watching. I've been Ethan7878, and I'll see you next time.